Hello students, today we're going to be talking about the image receptor and the image receptor exposure, what it looks like, and how best to correct issues with your image receptor exposure. So let's take a look here, some objectives. You need to identify image receptor exposure as a prime component of photographic properties influencing visibility of detail of the radiographic image quality. Differentiate between density and IR exposure. Describe the effects of IR exposure changes on the image appearance. What does that look like, okay? And differentiate between different noise types. So we're going to talk about that. We're also going to look at, describe the process of evaluating IR exposure, explain how each influencing factor affects the IR exposure. So we've talked about that already a little bit. We're going to go a little bit more into it, okay? Be a good review for you. Assessing IR exposure on various images. Recommend appropriate adjustments to compensate for variations in the influencing factors that affect the IR exposure. Okay, so quite a few objectives. Got a lot to get through. So some of this overlaps with the image class that you're taking, Image and Technique. So, and it's a review of what we've covered already to date in physics. So let's first talk about what is visibility of detail. It is what the eye can see on an image due to sufficient exposure and contrast. So really important to realize that there is more detail than what our eye can see. We are going to be covering the eye in the next couple weeks, so you'll be able to understand a little bit more the limitations of our visual acuity. Okay, so visibility of detail is what our eye can see, okay, but we have to have sufficient exposure and contrast in order to see the differentiation in absorption, okay, and the detail. So if we take a look at the IR exposure, there's two photographic properties that allow detail to be seen. So that is your IR exposure. You have to have some kind of exposure on your image in order to see differentiation, right? You also have to have contrast. Without IR exposure, you can't have contrast. So you need those two properties in order to be able to see an image, okay? So we've talked about this in the past, and we've talked about how brightness, old school, we used to talk about film, we used to talk about brightness, density. All these words are now out of date. You'll hear us old techs say it once in a while. We'll talk about the brightness of the image. But actually, brightness now in the digital world is a monitor function. So it's something that is changeable, okay, unlike film. We weren't able to change it. So brightness now, we shouldn't be using it. We should be using IR exposure, okay? So because brightness is a monitor function and we can change the brightness. It's the window level controls the brightness. So if we change our window level, our brightness is going to change, okay? We can make it darker or brighter, okay? The traditional term density is no longer used in the digital world, and we now call it IR exposure. It's still very difficult to get 20 years, 40 years of embedded language changed, but we are working on it. I promise you that. So as a technologist, we control the window level, okay? So the lookup tables, we've talked about that, will control, okay, what the image is supposed to look like. So when you get an image that pops up on the monitor, don't change the brightness or the window level, okay? Send it to the radiologist. Their monitors are totally different. So if some of the systems, if you change the window level, what happens is the doctor loses the range that they normally had. It limits their range. So if you just leave it alone, although it looks too bright or it's too dark, leave it. Send it. The radiologist will be able to correct that on their end. Okay? So back in the old days, we used to assess density and IR exposure on film. And you have to know that this H&D curve, which is the base plus density, and then we've got the shoulder. So we have the toe and the shoulder. And depending on how steep this line was how much contrast we had. So if it's a real lazy line here, it came way over, so way over here, it would be, we would consider that a longer scale. This is high contrast right here, high contrast. So you can see white to black, okay? Now with digital imaging, it's linear, so it's just one line. So don't change that window level, trying to adjust your image to make it look a certain way, because it doesn't need to happen anymore, okay? So typically we can only see with the eye, the naked eye, 0.25 to 2.5. So that was our base plus fog was the 0.25 all the way up to where it was black. We couldn't see any more contrast at 2.5. Okay, so those were our ranges, and that's all we had to work with. Now with digital imaging, you can see here on this lookup table, we have this linear line. So we can go from 0 all the way up to the max. Okay, so totally different than our curve here. So as you can see here, an image that's too light down here versus an image that's too dark up here. So we want to get an image, well, this is good, but an image right in the middle. So somewhere in this 0.25 to 2.5 range. Okay, so with digital imaging, we don't have to worry about that anymore. So we can adjust the image. The lookup tables will correct whatever we're off on. All right, so let's talk about overexposure versus underexposure versus overexposure. So the EI, so the exposure indicator number, is what we use, right? So the one thing that's important is that your underexposed image, you have quantum model or noise. Really, really important that you look and see that. Now, I see this all the time on swimmers views. So when you guys are doing the swimmers, right there where C7T1 is, it's too light. There's model, okay? So you don't have enough photons hitting. But your EI and the overall scanning of the image is still good. So you need to make sure that you take a look and make sure that you don't have model from being underexposed. You're going to look at your number as a reference, but as a skilled technologist, you need to be able to say, okay, I need the anatomy right here at C7T1, and I need to make sure there's no quantum model or noise there. Okay, so although the EI is correct, it may not be correct in the area that you are actually looking. Okay, back in the old days, we used to take a densitometer and we could measure the density to make sure it was at least 0.25 in that area. So that's how we checked to make sure that our image was properly exposed. So digital post-processing can eliminate excess information on an overexposed image. So if it's overexposed, you're just going to have like that, the scatter fog on there, but all the details still there. Okay, so the computer can, there's software programs that can take the scatter off, and it can adjust the image so it's contrasty so the doctor can see the anatomy. So it can adjust. So we typically don't repeat an overexposed image, but we have to repeat an underexposed image because there's not enough photons hitting that image receptor. So that scatter on an overexposed image is Compton. Let's talk a little more about lookup tables. So lookup tables try to change the image, image consistent regardless of exposure factors. So it uses automatic rescaling. I know you've heard that before. So automatic rescaling is going to take a scan of it and it's going to fix it according to what we'd like it to be. Okay, so it doesn't matter what exposure factors we used, it's going to try to fix the image to look like we programmed it to, no matter what. Okay, it can correct for overexposed. It has too many photons. Okay, the downfall is that you have a lot of scatter. Your image quality is, gray. You're not getting the contrast that you may need. Okay, it cannot correct for underexposed. So if there's no photons there, it can't do anything. There's nothing for it to process. Okay, so you have to repeat those. All right, so effects of image appearance. So multiple variables make radiography an art. So it's not an exact science, as we all know. It's definitely not. Variables usually balance each other out, so you have to make sure that you're using the proper KVP with the proper mass, and then the computers will help you fix anywhere where you're off by just a little bit, okay? Rules for changing and technical factors are guidelines. So we say use the 15% rule. Hey, you need to do 30% to see a difference of mass. So, they're guidelines, okay? It's not an exact science. So don't just say, oh, I have to change it exactly, double. I have to change it exactly 15%. So you're going to look and go, am I a little overexposed? Am I a little underexposed? Am I fully underexposed? Am I fully overexposed? Do I need to go more than 15%, more than doubling? What do I need to do? And that's where your technical abilities come in. Okay, that's where it's not an exact science. I wish it was. So here, effects on image appearance. So some of the things that we run into is noise. Okay, so if we look at our acuity, so we look at quantum noise, system noise, ambient noise. So if noise can be kept low, system works with lookup tables. So using AEC helps to ensure proper KVP and mass is used to reduce the noise. Okay, so we actually recommend that you use AEC when you don't know what's inside the patient's body. Sometimes there's a rod there, and sometimes there's pathology. We're going to talk about additive and subtractive pathologies. So we need to be able to respond to basically on what the patient has inside of them. So quantum noise, what is it? It's a lack of sufficient incoming data for processing. So quantum means number. Okay, so it's the number of photons. So quantum model is a blotchy, remember that salt and pepper looking image where there's just not photons hitting. So you can see the spots of black where the photons hit, and then the white part is where there's no photons. Okay, so normally what we'll do is we'll increase our mass for that. Okay, as long as you have the proper KVP, we'll increase our mass to accommodate for quantum noise. All right, or quantum models, same. So there's system noise. So inherently in all the systems, there's electronic components in the system, and those can add noise to your image also. So if you have some kind of weird artifact on your system, or you can see it on your image, it might be system noise. There might be a bad wire, or something vibrating in there that shouldn't be. So you'll definitely need to call out a service engineer and have them look at your image. Okay. There's ambient noise, which is background radiation. So we have to deal with that also. So there's a lot of different things that can affect your image, and you being able to identify, okay, is that from not enough photons, or is that from the system where there's something wrong with my, with my processing? And then we have to deal with the ambient noise also. Okay. So here, factors affecting IR exposure. So as we've already talked about this in the past, but let's review it, okay? So controlling or influencing factor, mass as the controlling factor. So if you are looking to change your number of photons, you are going to deal with mass. If you need to increase your IR exposure, you are going to change your mass. Now your KVP is going to be set based on the body part. Okay, and the thickness of that body part. So the energy, that's a penetrating power. The mass is how many photons do you need to expose the IR properly. So when you're using AEC, AEC is going to measure the number of photons coming through. So you're going to set the KVP will be set, the MA is set, and the time is the variable. Remember that? So it's going to run for however long it's going to take for the image receptor to receive the proper amount of photons, which is your mass. Okay, so influencing factors for your IR exposure. Your SID is going to affect your mass, right? So we have that divergent beam, so the inverse square law. So the further away we go, it's d squared, right? So we have to increase our mass. If we come closer, then we're going to decrease our mass, right? Also, patient factors. So if you're dealing with air versus bone, there's a big difference in the subject contrast or the subject density inside the patient. So that's going to change how many photons are absorbed or how many photons are transmitted. Okay, so we also use the mass reciprocity for IR exposure. Now the thing is, the mass reciprocity fails for extremely short exposures. So it doesn't apply well sometimes to digital systems because digital systems are super fast. So it doesn't always work, but it's a good rule of thumb. Okay, digital receptors have a linear response to exposure, where film was nonlinear. So I showed you those graphs. So we have the H&D curve with the toe and the shoulder for film, and we have a linear when we talk about our digital receptors. Okay, so there's a lot more room to fix errors with the digital system compared to film. Changing the mass. Now, we've talked about this prior, a minimum of 30% change is needed to see a difference in your IR exposure. Now, your book does talk about a range from 25 to 35. Great, 25 to 35% you need to change in order to see a visible IR change, okay, in density. So we typically just say 30%. Make sense? All right. So the thing is, that's just to see a visible change. We want to see big changes, right? So when we're dealing with mass, we are going to half it or we're going to double it. Don't be shy. Go for it. Half or double. Now, if you're close and you think, I could use a little more mass, you try using the 30%. Okay, so you're going to see an increase, a bump at 30%, okay? But it's not going to be too dramatic, okay, as halving or doubling. So, but try it. Don't be shy. Try the half or double. You'll be surprised how it doesn't swing your EI that much, okay? So, repeats, seldom justified for greater or less than 30%. So, if you're going to do it, do it. Go half or double. You need to check your exposure indicator and have that be your guide on how much you're going to change it. Okay, so don't just jump in and say I'm half or doubling when your EI is just barely overexposed. You know, if you halved it, yeah, you'd fall in range. You'd be on the lower end of the range. So you got to be careful that you're not too low because you're going to have quantum model. So kind of look, 30 to 50%. So don't be shy. Don't be shy. And this is where your skill comes in. Okay, this is where skill comes in. So with this slide here, we have technical factors that affect the exposure. So image quality is a function of total exposure to the image receptor. Exposure is a combination of many factors. So we know that. So our main factors are KVP, mass, distance, right? So those are the big ones. Now, there's other things that go into play that also take up photons, right? They eat up our mass. So SID, changes in SID do affect our exposure also. Filtration, so remember it's taking out those lower energy photons, so it's absorbing up our mass. Grids are absorbing photons in the remnant beam that are scattered, so it's taking up photons. Collimation, as we collimate tighter, there's less photons. Right? So your IR sensitivity also. So if your IR image receptor is not very sensitive, it's going to take more photons in order to expose it. Okay? So body part. How thick is your body part? We also have to deal with the anode hill effect, right? So remember there's a 45% swing due to that anode hill effect. And then our focal spot. So we're going to go into the focal spot. We haven't talked about that yet, and it's called focal spot blooming. So we're going to talk about that in a few slides from now, okay? So using a large focal spot versus a smaller focal spot, okay? So mass and IR exposure. So as we talked about, mass is the primary controlling factor. You want to use that first. Don't go to KVP, okay? Direct proportional to exposure. So if you go up, your exposure is going to respond. Now, ideally, IR exposure, 1 MR change is 33% mass change. So that's in your textbook, okay? Marginal noise on image generally requires a 30% increase, okay? IR exposure best controlled using AEC and technique charts. So make sure your KVP is correct and use AEC to control your mass. Okay, it's really, really hard to determine what mass to use on each person. Now we could guess, kind of get in the range, but AEC is going to do it for us. And then with the lookup tables, it's going to fix everything. Okay. So let's talk about KVP and how it's an influencing factor. So KVP controls the average energy of X-ray photons at the anode target for any given mass. KVP affects production of scatter. Changes in KVP varies beam quantity and quality. Remember that? So it has a big impact on our IR exposure. So it does give us more photons and a higher energy beam as we go up in our KVP. So we have to be very careful. And the byproduct of that is scatter. So it's going to degrade our image. So we have to be very careful, okay? Thresholds for KVP should be used based on the body part and the K edge of the detector. Now, some detectors are more sensitive than others. So we haven't really talked about that, but I think in your image and technique class you are. So the image receptor can have different speeds. And depending on the speed of your image receptor, the higher the speed, the faster the image receptor, but also the less detail you're going to get. So a slower speed system is going to give you better detail, but it's going to require more mass. All right, so KVP can influence the shape of your histogram, so you have to be careful on your lookup tables. So you got to be in the right KVP range in order for your histograms for your lookup tables to work properly. All right, so small changes can have a profound impact on your exposure. So we've talked about this, the 15% rule for KVP, right? Increasing by 15% doubles your image receptor exposure. Decreasing by 15% halves the exposure. So the 15% rule can range from 15 to 25% depending on the starting KVP. So the lower you are versus the higher you are, it does vary, okay? So just so you guys know, 15 to 20%, 25% is the range. Typically, we just use 15%. Okay, so it's not an exact science. We've talked about that. So it's an art. So typically you use the 15% rule, works every time, 99% of the time. All right, so let's talk about KV still. So if we have significant changes in KVP, it impacts the contrast. So scatter and secondary can be too much for proper histogram processing. So if you have too much scatter, you use too high of a KVP for the body part, you're going to have a lot of scatter on that IR, and the histogram is going to struggle. It's not going to know exactly what to do, okay? So impact of KVP change is dependent on the KVP level, okay? So 4 to 5% KVP change gives you a noticeable change, noticeable at lower KVPs. So if you have a real low KVP, a 4 to 5% change is going to be seen. Okay, so we talk about that. So that's typically what we use is we say, okay, 4 to 5% KVP change, you're going to be able to see a difference, a noticeable change, okay? But if you're at a really high KVP, a 10 to 12% KVP change is what's needed to be noticeable at the higher KVPs, okay? So typically we just say the 4 to 5% in order to see a noticeable difference. It's not common that we're working in high KVPs. So we're talking about 110 over 100, you know, is where you're going to be 10 to 12%. So typically we're under that, so we just say, you know, 4 to 5% to see a noticeable change. So, but do know that it is at higher KVPs, it needs to be higher percentage in order to see the difference, okay? KVP change is not recommended to control image noise, so we don't recommend it. If you are underexposed with your IR, you're going to use mass, okay? So you're going to use KVP just to make sure you have enough energy to get through that body part. So generator configuration. So it does affect, you know, the energy of your beam. So only considered when changing from single phase, multi-phase, kind of the same, like I clumped them together for you, okay, to high frequency. Okay, so if you take, you know, you've got your 6 pulse, your 12 pulse, you know, single phase, all that, okay. We're just going to say single phase, multi-pulse, and high frequency. So more accurate to change mass to maintain eye exposure. So if we look and we go from single multi-phase to high frequency, what you're going to do with your mass is you're going to multiply it by 0.5, right? So we're going to take it down, okay? So we're going to get a lot more photons coming out of a high frequency, okay? So we need to reduce our mass down by 0.5, okay? You're going to multiply it by 0.5, so half. With a high frequency to a single multi-phase, you're going to multiply by 2. You're going to take it up 2 times what it would normally be. Okay, so I used to shoot a hand at 55 at like 8. I mean, I was on a single phased. So yeah, it was crazy. So we shoot it at 4. That makes sense, right? So if we're on a high frequency generator, you shoot it at 4. But if you're shooting on a single, I'd shoot them at 8. Is that crazy? An elbow would be like at 20. Crazy, crazy. All right, so we've come a long way. That's what I'm trying to say. All right, focal spot size. So this is the one I told you I was going to talk to you about. So we haven't talked about this before. It will not affect the IR exposure in a properly calibrated unit. Now, they've compensated for this, okay? Now, if your unit is not properly calibrated, it can vary by 30%. 30% going from small to large. 30% in your IR exposure. That's crazy. All right, how does this happen? So there's blooming. It results from high MA selection. So a large focal spot where the beam is not focused by the focusing cup can cup as easily as the small. So you have that. You have what's called, the thermionic emissions. You have all those electrons just floating out there right off of the filament, right? So you have the focusing cup that's keeping them all in the area. When you have a large, it's easy with the small, but when you go to the large, it struggles more so, okay? We call that blooming. So it can't keep all those electrons in the area because the focal spot's so big. So when you actually expose it, there can be up to a 30% variation. So the manufacturers have compensated for that, and they've fixed it so that it looks the same whether you use small or large. So we don't have to think if we're using a small or large focal spot and adjusting by 30%. They do it for us. Thank goodness, right? Proper calibration on a regular basis keeps focal spot issues under control, thank goodness. Calibrated systems with continued blooming may warrant X-ray tube replacement. It means something's not working and you need a new tube. Okay, so if you notice that if you're going from small to large and you're shooting an elbow, let's say, and you're using a small focal spot and then you go to a large focal spot, if it changes by 30%, you might need a new tube. Okay, or call out the service engineer, because if you go from small to large, it should look exactly the same. They've calibrated the machine to fix this. All right. Anode Hill effect. So we've talked about this in the past also. So it's due to electrons interacting in the anode surface, okay, alters the intensity of the beam across the cathode anode. Remember fat cat. So the IR exposure can vary 40%, 45% from the cathode side. So heavier on the cathode side. Remember fat cat. So between the cathode side to the anode side, it can vary up to 45%. So really important that you remember that and you use that to your advantage, okay? So if you're doing a foot, you want to put the fat cat, so the cathode side, on the thicker portion of the anatomy, okay? So use it to your advantage. It's more pronounced with a wider collimation. So if you're not collimating, you're going to see it more so than if you're collimating in really tight, okay? All right. And you're going to see variations in intensity more extreme at the periphery of the image. So if we're looking here and we are going back to the inverse square law and the exposure maintenance formula, okay, or direct square law. See, either name is used, okay? So if we're looking at SID and OID, so with inverse square law, as you guys know, it's intensity 1 over intensity 2 is equal to distance 2 squared over distance 1 squared. Okay, so this is looking at changes in the intensity with distance. So if we're looking at the mass and changes in mass with distance changes, it's mass 1 over mass 2 is equal to d1 over d2 squared. Okay, so they're directly related. Okay. Filtration. So if we're looking at filtration, it's inversely related to IR exposure. So the higher you go with filtration, so up with your filtration, you go down with your exposure, right, on your IR. So increased filtration will decrease IR exposure. Increased filtration will increase the average energy of the beam, but reduces the intensity or the quantity. So if we take a look and we have here, this is low filtration versus higher filtration. It is absorbing that filtration, some of our quantity. So this is quantity here, and you can see that we shifted to the right. Okay, so without filtration, with filtration. So you can see that we have reduced our quantity and we made it a harder beam. So here's our peak right there versus our peak here. All right, so beam restriction, inversely related to IR exposure. So increased beam restriction decreases IR exposure. So reducing the total amount of remnant radiation striking the IR, which reduces scatter and secondary radiation. Number one thing you can do is collimate, okay, to reduce scatter and radiation dose to the patient. So dramatic changes in collimation require a mass compensation. So if you're going to collimate in super tight, you have those lead shutters. Remember, they're lead, so they're absorbing the photons. Normally our beam big round beam. So we're taking it and we're using those lead shutters and we're blocking those photons. So that is taking the quantity out. Okay, so we need to increase our quantity. Okay, so tight collimation can impact the histogram. So you have to be very, very careful when you're using too tight of collimation, because the histogram's not going to see the exposure on the IR that it's used to seeing. So in digital especially, you need to be careful that you don't collimate in super tight. We used to shoot a finger. I mean, it would be, you know, 1/2 inch by 2 inches, and that would be all we would do. Now with CRDR, the systems wouldn't know what to do with that image. So it's got to be big enough where the system can read the image, okay? So here, anatomical part. So patient is a prime attenuating factor of the beam. It depends on how thick the tissue is, what the tissue is made up of, right? So what's the Z number, and how tightly packed are all those atoms, right? So inverse relationship between the IR exposure and the part thickness and density. So the thicker or more dense the tissue, the more it's going to absorb your photons, therefore your EI is going to change, okay? So pathology also. So we're going to go into pathology here and talk about additive versus subtractive, okay? So if we have an additive, so what it's doing is an additive pathology is something that is going to decrease your IR exposure. It is like a calcified tumor. So additive is adding to the normal density of the body, okay? Additive. Where destructive is where it is taken away. So it's eating away what normally would be there, okay? So we also use contrast material, and that is going to absorb photons also. So if we are looking here, we have part thickness variations with tube angles. So if you have an angle that's greater than 15 degrees, it can give you up to a 30% exposure difference on your IR. Crazy, huh? So as you can see, here versus here, this has got further to travel and it's going through more anatomy. Okay, so it's greater part thickness compared to here. Okay, so same thing here. So just keep that in mind when you're doing angles more than 15 degrees, you're going to see changes there, okay, with your intensity on your IR. So casts. Now casts are really interesting. If you use a cast, just a fiberglass cast, and you're x-raying someone, don't change your technical factors. Now if you have one of those clay casts and it's wet, you're going to have to go up with your technical factors, okay? But if it's fiberglass, don't change it. If the cast is dry, don't change it. Your factors should stay the same, okay? So if it's wet, go up, okay? Grids, oh boy. So scatter radiation normally hits the IR and increases the exposure. So we're using a grid. It's going to absorb those photons that would normally hit our IR, right? So we have exposure is inversely related. So increased grid ratio decreases IR exposure. The grid conversion formula is right here. So mass 1 over mass 2 is equal to grid conversion factor 1 over grid conversion factor 2. And we talked about grids, and we talked about how if you have a 6-to-1, 5-to-1, 8-to-1, 10-to-1, 12-to-1 grid, and what those grid conversion factors are. Okay, so if you have an 8-to-1, your grid conversion factor is typically a 4, so you can plug in the numbers. A 12-to-1, remember, it's, now my mind is going blank, a 5, 6. So I'd have to look it up, but it's a gauge, okay? So you can plug in the numbers and see exactly what your mass should be. Okay, so if you don't know the exact number, you kind of have an idea, okay, if a 8-to-1 grid is a 4, a 6-to-1 is a 3, a 10-to-1 is a 5. I think 5 is the max. So you can 5 times what it normally would be, okay, multiply by 5. Okay, so that will give you a rough estimate when you're in clinic, so you don't have to pull out a calculator and solve this. But if they ask you to solve it on your national exam, this is your formula. Now it's directly related. So mass 1, grid conversion factor 1. Mass 2, grid conversion factor 2. It's not squared. Okay, so you just plug it in. It's going to give you the new mass that you need for using that grid. All right, image receptors. So let's talk about those. So we've got film, screen, and digital systems. The speed of them do impact your IR exposure. So the exposure index numbers are useful parameter for digital imaging. So you look at the relative speed, so RS. Okay, so I don't know if you've covered this yet or not, but I'm going to talk a little bit about how the speeds do affect the image receptor. So it's a useful parameter for film screen combinations. So DR receptor speeds generally are RS 400 or faster. So relative speed of 400 or faster. Some are as fast as 800. So what happens is with the lower, slower RS numbers, the better detail typically you have. The faster, so like in trauma, we'd be using an RS 800. Okay, so if we have an 800 system, we're going to have really fast processing, which is fantastic, but our image quality is not going to be as good. So I'll go to some of your sites and I'm like, gosh, all your images are kind of blurry. Why are your images blurry? And it's because you're using a really fast system. Where if you have a slow system, you're going to get really good detail. So like in an orthopedic center, you're probably going to be on a 400 system, so that you can get that detail that the doctors need, okay, looking for hairline fractures. But an 800 system, all the images are a little blurry, at least to me, the trained eye, right? All right, so this is our last slide. So let's take a look at it. Now, we're going to start doing what's called an up and down chart. So we're going to start focusing on what changes affect what, okay? So if we take a look, and they're talking about density, so you know that this is old. So change it to IR exposure, okay? So if you increase your mass, you're increasing your IR exposure. Makes sense, right? Doesn't have anything to do with contrast, doesn't have anything to do with your recorded detail, and it has nothing to do with distortion. If you increase your KVP, you're increasing your density or IR exposure. You're decreasing your contrast. Remember, you're getting a longer scale. Has nothing to do with recorded detail and distortion. If you increase your SID, you're decreasing your IR exposure. No change to contrast because your KVP hasn't changed, right? So you're increasing your detail though, because you don't have the divergent beam that you had. So you don't have as much penumbra. So you're increasing your detail and you are decreasing your distortion. So the beam is not as divergent, it's going through the patient straighter. So you have less distortion. So you see how this works? So it's kind of cool. So if you take your increased grid ratio, you decrease your IR exposure, you increase your contrast, no effect on recorded detail and no effect on distortion. Now you're like, no effect on recorded detail, but it's so much clearer, the image looks so much better. The detail was always there. It was just underneath a layer of fog. So you couldn't see it. It was still there though, because all the scatter radiation was on the top. It's like a cake. So you have a cake and it's frosted. So the frosting is the scatter. The cake's still on the inside, but once you remove the frosting, you can see the cake. Okay, so this is called an up and down chart. And this up and down chart, we are actually going to be doing a chart. You're going to be filling it out. So we're going to talk about it. We're going to go through it. I'm going to make sure you understand it because it will be on your final. Okay, so we're going to start working through the up and down chart. But if you stand back and you think about it, I need you guys to start processing and putting all of this together. Okay, so that's your lecture for today, and I hope you enjoyed it.